All right, welcome everyone. I am JJ. Let's tackle an example problem. So we have a 300-pound block is supported by a rope which wraps around 1.5 times around a horizontal rod. Our coefficient of static friction between the rope and the rod is 0.15. What's our range of values of P? We're going to stay in equilibrium for this. So if we are to break equilibrium, we could break this in one of two different ways. Either we could be pulling down so hard on this rope that our block starts to go up, or we could be pulling so lightly that the block barely just starts to drop down. One of those two things could happen in there. So we just want to look at both of those. Let's come in and do our first one. Let's say our block is about to lower. Block is about to lower. And we can come in and analyze this. Then we'll come down below and say, well, what happens if that block is about to raise? Block is about to raise. So the top, the block's about to start coming down. Down here, that block's about to start going up. Either way, we're using belt friction on this. Our belt friction equation is T2 equals T1 e to the mu beta. T2 is the force in the direction we're about to move. T2 is the other direction's force. E is Euler's number. It's a constant. There's an E button on your calculator. Mu is our coefficient of friction. Beta is our contact angle. So let's kind of start trying to draw just a loose picture out for this. So for all of these, I know my mu. Mu should get me to, mu is given. It is 0.15, 0.15. And beta, well, beta is going to be equal to, if I go 1.5 times around, one full circle, and then an extra half time. If every circle is 2 pi, 1.5 circles would be 3 pi. Always getting this in radians. Beta is 3 pi. And that's going to be true either situation that we work with in here. Let's come in and draw just a loose cross-section that we have here. If I have my rod, and I'm looking down it. On one side, I have a 300-pound force. On the other side, I have P. And I can set this exact same picture up down below. On one side, I have 300 pounds. On the other side, I have P. But what I need to figure out is which one of these is T1 and T2. And it's going to be different in each of those. So if I'm about to lower that, let's come in and sketch in our motion on this. If that block is about to lower, we're going to spin counter or clockwise around this. We are going like this for our motion. Motion. Which means when I come in and I figure out T1 and T2, my motion should point towards one of these forces. It's T2, where I'm about to start moving towards. This is T2, which means the other side is T1. T1 equals P. And I can come in and use my belt friction equation then. T2, 300, equals T1, P, times E to the mu, 0.15, times beta, 3 pi. Or I can solve for P, and I would get P is 72.97 pounds. And that's one of my equilibrium boundary conditions. Let's check our other one then. So down below, we are saying we're about to start raising that block up. That means this side is starting to come up. We're swiveling this direction. This is now our motion. If that's our motion, really we are just changing T2 and T1 in here. That 300 is where I'm coming from. It's T1. The other side where I'm heading towards my impending direction of motion is T2. Or is T2 is P now. So let's solve for P. So I can say T2, P, equals 300 T1 times E to the 0.15 times 3 pi. 3 pi, not 35. times 3 pi. Or solving for P, we get that this force that's going to start to lift that 300-pound block up is 1,233.36 pounds. So if I can pull with 73-ish pounds, I'll prevent it from dropping. If I can pull with 1,233-ish pounds, I'm going to be able to lift that box up. Anything in between there, though, I'm in equilibrium for this. So really my answer on this, what's my range of values for equilibrium, would be I get equilibrium when our smaller value in here, 72.97 is less than P, is less than 1,233.36 pounds for both of those. But that would be our answer in here. I'll put parentheses to the pounds on everything. But that's really all we're looking for in that. How do we maintain equilibrium? If we could get motion happening in here, a lot of times we don't want motion happening. What could happen to keep us in equilibrium? Hopefully this is a useful video for you. If it was, hit those like and subscribe buttons, stick around, watch more videos. Let's get you an A with JJ.